Hi everyone, Dr. Vaughn, and I'm going to do this one problem from chapter 15. I'm going to do number 15.8. Got a little Beethoven playing in the background, so if you hear some music, that's what's going on. Symphony number 9. Anyway, I chose number 8 as opposed to number 7 because you got the answer to number 7 in the back of the book, and hopefully this will help you with all of the problems in chapter 15. So this is about cigarette consumption before and after they did this anti-smoking film. So the question is whether viewing the anti-smoking film actually reduced the average amount of daily cigarettes that these teens were consuming. Although this seems like a lot of cigarettes, 28, 26. So anyway, maybe it seems like a lot. But whatever. So we have these before and after kind of scores. And we're going to do this paired samples t-test. So again, we have two groups, but they're linked together because of the patient number. We couldn't sort these. So what you do for a paired samples t-test is you actually take the difference between them, and then you do a single sample t-test on the difference. And you're making a comparison because if the means of the two groups are the same, then the difference between the groups would be 0. And so that's going to be basically our null hypothesis. But we're going to go through all of the steps very carefully. I've actually pre-populated some of these back on here to the whiteboard. And you'll be surprised to see I actually figured out a way of typing little notes on here. So we started with step 0, paired sample t-test is the test that we're choosing to do because we have two groups. They're paired together, and this is that before-after very standard kind of model. Alpha equals 0.05 is given to us in the stem of the problem. We are going to do a one-tailed test. And I know that because when I look at the statement of the problem, which is here in the book, it says they wanted to determine whether a new anti-smoking film actually reduces the daily consumption. They don't want to know whether it increases the daily consumption, only that it reduces. So that's a one-sided test. It also kind of gives you a clue down here in this note when deciding on the form of the alternative hypothesis. Remember that a positive difference score reflects a decline in cigarette consumption. So what we're looking for in the alternative is that this D, which is the difference between them, is actually positive. Because if D is positive, that means a decline. So that's going to be our alternative hypothesis. So the alternative is that the mean difference is positive. And the null hypothesis then is that the mean difference is not positive, in other words, less than or equal to 0. And with these paired samples t-test, when you're taking the difference, you're always comparing to 0, unless, again, those weird cases, which you're not going to run into, where you expect the difference to be something, kind of like we talked about in the 2 samples t-test. All right, so that's kind of your steps 1, 2, and 3, one sample test, and the way in which we set up our null and alternative hypothesis. Now we're going to use this t observed value formula. You can get this right from the book. If you just scroll up above your problem, you get the formulas for the t observed value right here. It's the mean difference minus the hypothesized difference, which is going to be 0, divided by the standard error of the difference, where the standard error of the difference is the standard deviation of the difference divided by square root of n. This is very, very much like our one sample t-test. It's just we're using the mean of the difference of the paired values together and the standard deviation of the paired values given together. So they didn't give us those mean of the differences or standard deviation of the differences, and we don't know the population standard deviation, so we're using a t-test. But they did give me the raw data, and so I typed it over here into Excel. Here's the smoker number. That's just an index, the before and the after. And so the first thing that I want to do is compute the differences. And so for the differences, I'm just going to do equals, and I'm going to take the number in the B column and subtract the number in the C column. So this smoker went down by 2 cigarettes a day before and after watching the film. And then I can just copy this down. I don't need any of those dollar signs. And you see this person actually increased their cigarette consumption. These two stayed the same. This person went down a lot, but most of them were in that 2, 3 kind of range. So these are the differences. Now I want to compute the mean and the standard deviation of these differences. So the mean of the differences, I'll just do equals average and click and drag through those differences. And I'm going to compute the standard deviation of those differences. So equals stdev dot s, a sample standard deviation of those differences. and I get these two numbers, 1.5 and 1.690309 for the mean and standard deviation. All right, so that's really all I have to use Excel for, although I'm going to show you how to do this in Excel after we finish part A here. So let's go back over to our smartboard and actually figure out this t observed value. So we'll calculate it just by hand. So our t observed value then would be that mean difference, which was 1.5, minus the hypothesized difference, which is 0. We're saying that under the null, there's not going to be any difference between their smoking habits before and after the film. And I'm going to divide by the standard deviation divided by the square root of n. N is 8. There's 8 pairs. There's 16 data points, but they're split into 2 paired groups. And so the n here is just the number of paired groups at 8. So I'm going to take this standard deviation divided by the square root of n. The standard deviation, 1.69. Let's just round it off to that. And divide by the square root of 8. So I'll do a little calculator work here. 1.69 divided by the square root of 8 is 0.597. I'm going to do the reciprocal of that and then times it by 1.5. So I get 2.51 approximately. All right, so now we got to do step 5, which is to look up those critical values. And at the 5% level of significance with 7 degrees of freedom, because our degrees of freedom is again going to be the number of pairs, which is 8 minus 1. So I can go to the back of the book and I can look up that t critical value, and there's only going to be one of them because I'm putting all 5% into one tail. Now, I can also use Excel to actually figure out what that t critical value is going to be. And then I'm also going to show you how we can use Excel to actually calculate the p-value, which is part B of this problem, instead of using that table at the back to kind of interpolate and make a guess about where the p-value would actually lie. So to figure out this t critical value, I have to remember that I'm doing a one-tail test. So I want all 5% to be up in one tail, and it's the upper tail because I'm testing the alternative hypothesis that the difference is positive. So I want the line where it divides 95% below from 5% above. So I can use this equals t dot dist, t dot inv, where I'm going to put the 0.95 below, and then I'm going to put in the degrees of freedom, which is 7. So that t critical value is going to be 1.89. And it's not plus or minus, it's only the positive because we're doing a one-tail test on the positive side. So in this case, our t observed value is above the t critical value. And that means that we are in the rejection region. The 2.51 is up here somewhere. The 1.89 is that cutoff line. And so our observed value is larger than the cutoff line. We are in the rejection region. So we reject the null hypothesis. And our step 7 in just kind of the straightforward sort of approach would be to conclude that watching this film did have an impact on the average number of cigarettes that was smoked by these teens. In general, this difference was positive, meaning their smoking habits did decrease after watching the film. All right, so I'm not going to write that out in words on here, but what I wanted to show you is that we could use Excel to kind of do all of these steps for us in the case that we have the raw data. Instead of having to calculate the differences and the mean and the standard deviation and use my calculator over here and then look up the p critical value and all that other kind of business, when they give me the raw data like this, I can just use the data analysis toolpack. So I'll go to the data tab and we'll see if we get a consistent result. We'll go to data analysis and I'll go to T for paired to sample for means. And now I'm going to put the first set of scores with or without the labels, but make sure you check this box. So I think I'm going to grab the labels this time. And then for variable 2, I'm going to grab the labels here. And I did use the labels, and the hypothesized mean difference was 0. The alpha is set to be 0.05, and I'd like to put the output here on my table, maybe down here somewhere. Right, so now that I have all these things set, I'll press OK, and you get this output for your t-paired 2 sample for means. We got the mean of the before group, the mean of the after group, the variance of the before, variance of after, 8 of each, they're paired. The hypothesized mean difference, the degrees of freedom is 7. Here's their calculation of the t-stat, 2.50998. Let's say how that compares. We got our t observed value, 2.51, 2.51, so those turned out to be the same. And then they actually give you these p-values, and if you widen this just a little bit, you'll be able to read it better. This is the one-tail p-value, 0.02. So from Excel, we're getting that p-value of 0.02, but I'm going to show you how to compute it without using the data analysis tool pack as well, but we still need to actually use Excel. And here's the critical value. This is the thing that we could have looked up in the back of the book. It's also the number that we calculated up over here, 1.89. It shows up automatically in this table, so I didn't have to type in this t.inv kind of formula if you use the data analysis tool pack, and you can just interpret the results from the table. So now I'm going to show you how to actually calculate this p-value, the 0.020199. So what we're going to do for the p-value is draw another one of these pictures, and this time I'm going to put the t observed value on there. All right, so here's my picture. And the t observed value is here at 2.51. The p-value is the probability of getting an observation more extreme than what you observed. Now, ordinarily, we double that because it can be more extreme on either side, but this time we're doing a one-tail test. And since I'm doing a one-tail test, the more extreme only appears on one side. So the p-value really is just the area to the right of this value. So what I want to do is use that t.dist to find the area underneath the curve, and then I'm going to do 1 minus to get the area above, because remember, Excel is going to always give me the area below when I use the t.dist function. So let's see if we can't come up with that same one-tail p-value, 0.020199. And to do that, I'll just write here. My function that I would use is equal 1 minus, because I want the right side instead of the left side, t.dist. I want the regular t distribution, not the inverse. And in the x variable, I'm going to put in that t critical value, that t observed value, which I don't have written on my screen, but I could either pull it off of this table or I could just type it in because I did that calculation, 2.51. So let's just type it in, 2.51. And then I want the degrees of freedom, which was 7. And then we can put that cumulative true or false. You can just click on it, or you can type the word true in all caps. And I'll press close parentheses. 1 minus t.dist, parentheses, 2.51. That was our t observed value. 7 degrees of freedom and true. And there you get that same p-value, 0.020198. All right. And then finally, if you were going to do this by using the tables in the back of the book, you'd have to take this t observed value, go find, with 7 degrees of freedom, look in that table, and it's not going to give you 0.02. It's just going to say it's somewhere between 0.01 and 0.05. They'll give you the 0.01 number, they'll give you the 0.05 number, and you have to just kind of interpolate that it's somewhere in between those two. All right, so in this case, we rejected the null hypothesis. We made a conclusion that showing the film did actually decrease the consumption of cigarettes amongst this population of teens. I think I'm just about done with this video, but let's just take a look. We did part A, we used the t-test. We did part B to specify the p result. What I wanted to also comment on is this p-value is consistent with our other determination about comparing the t-critical value to the t-observed value. But we could also just say p is low, p is less than alpha, and if p is low, reject the HO. So we're going to actually reject the null hypothesis by simply looking at the p-value, never having to calculate what that critical value is. In part C, it says, if appropriate, construct a 95% confidence interval, and then what might be done to improve the design of this experiment. we'll just kind of talk about this 95% confidence interval. You could do the Cohen's d part, scroll up in the book and find the formula for it. But to find our confidence interval, it's not on this table over here, but we could do this also, the confidence interval for the difference. So what I'm going to do for the low side and then the high side of that confidence interval is I'm going to take the observed difference. That was this one. 1.5 was our observed difference. And we're going to subtract the t critical value, which we got from right here, one tail, times the standard error. And the standard error is that number that we got right here, standard deviation divided by the square root of n, actually. So I should just type standard deviation divided by square root of 7. All right, so we got the observed mean difference minus the standard error times the critical value with the minus. That should be the low end. And for the high end, I'm just going to take all this same formula. I'm going to go up here, just paste it in, and change that minus to a plus. All right, so my confidence interval goes from 0.289 up to 2.7, but notably 0 is not in that interval. So the true mean difference is greater than 0. It's not 0 because 0 is not inside of that interval. So that's the first part of C. You still have to do the Cohen's d. Again, scroll up, find the formula, plug it in, and then just talk about something in part D about improving the design of this experiment. All right, well, I hope this has been helpful to you. This is, I'm going to sign off and go back to listening to Beethoven. Have a great night.